Today in the 1107 labs, what we're going to do is start working on the physics of rotations. Rotations of rigid bodies, to get more specific. And you should know before we start that a rigid body is just something that doesn't deform, it's not floppy, it's not like a noodle. It stays, everything in it stays in the same shape as it does stuff, and it never gets deformed or twisted or anything like that. There is physics that covers that, but it's beyond what we're doing today. Today we're just talking about things that, in addition to having a location, they also have some sort of orientation, and the orientation can change. And that's the physics we're going to be talking about for the last section of 1107. You should also know that this rotations we do here is really a subset of a bigger theory. The rotations we're going to be talking about are the kind of rotations that a wheel does as it turns around an axis. And we will not be talking about the more general rotations where things move through space and they can be tumbling and rotating and all sorts of complicated things. If you want to see a nice video of those, look at the Richard Garriott video filmed in the space station, and he will show you how things move in zero gravity where they can twist and rotate. We can see all that stuff. So we're doing kind of a limited version of rotations. It's enough to talk about a wheel rotating. If you want to go much beyond that, you need more. Anyway, the first problem we have is just specifying a rotation. Rotation isn't like a position, it's something twisting, and we need a rigorous mathematical way that we can write down what a rotation is. So what we do is say, here's our rotating object, and it rotates around an axis. And to measure a rotation, you have to pick some orientation that is rotation 0. So if you twist this wheel so that the point that was down here now moves up to here, you have rotated it through an angle, theta, and theta can be measured in several different ways. You can measure it in degrees, in which once around is 360 degrees. Degrees are actually a remnant from the old Babylonians, way back when they invented degrees, and there's a lot of stories about that. A more physically convenient way to measure rotations is in radians. And radians go from 0 to 2 pi. 2 pi is once around in radians. This turns out to be mathematically much easier to deal with. And so in physics talk, if we don't say otherwise, we mean radians. Your calculator can doubtless accommodate both, and somewhere on it is a switch to go from one to the other. Okay, so that's specifying a rotational orientation. If you want to talk about some other rotation, and this little dot goes all the way up here, then that is another angle that gets added on it. Angles are usually known as Greek letters. That would be a Greek phi letter. So that's how we talk about an angular orientation. Now, going from one angle to a different one is obviously a kind of angular displacement. We have the same concepts coming up over and over. And an angular displacement, which I'm going to call delta theta, a change in angle, that takes some amount of time to happen. So if we take the change in angular position and divide by the change in time, we're getting something like a velocity. And this is, in fact, known as angular velocity. And it's generally done with another Greek letter called omega. It looks kind of like a W, but it's really a small omega. We can derive some formulas from this. If something moves at constant angular velocity, then the change in theta as time goes by is just omega times the amount of time that goes by. There's a kinematic formula for rotations that kind of falls out of just doing that one backwards. There's also an angular acceleration if angular velocity changes. So if we have a change in angular velocity, and that takes time, we divide that by t, and that will be an angular acceleration, which is known as alpha, yet another Greek letter. And it behaves just like a regular acceleration. And if you're in a realm where you have constant alpha motion, then the change in omega equals alpha times the time that goes by, and the change in position is whatever omega is at the beginning times the time plus 1/2 alpha time squared. And all these equations should look really familiar. The basic mathematics is the same as what we did back in the beginning of the course. These equations fall out of the same derivations. Everything is mathematically the same. They do mean different things, and there is one big confusion to worry about, which is angular acceleration and the acceleration of something moving in a circle. Those two are easy to confuse, but they are different. Angular acceleration is acceleration around the rim, and the acceleration to make it move in a circle is toward the center. They're in different directions. Okay, one more place where there's a difference is in the relationship of angular and linear variables. If you're on a wheel and you're spinning around in a circle, this little dot on the edge is obviously moving, and thus it has some velocity, a linear velocity. The linear velocity is tangent to the circle at any moment, and its magnitude is given by v tangential equals the radius of the circle times the angular velocity. This only works if you measure angles in radians, and this is why radians are so nice, because they let you do this. The velocity at any moment is always tangent to the circle, and as it goes around in a circle, its velocity changes. And it's actually true that the centripetal acceleration is what's changing this velocity. So a centripetal is toward the center, and that's what makes v change as it goes around. Now, if something's also speeding up as it goes around, then it has an acceleration tangent to the circle as well, and we have an a tangential, which is given by r times alpha. And that acceleration is not toward the center, that's accelerating in the same direction as the velocity. So this is a tangent. There are two different accelerations happening for things moving in circles. If it's moving in a circle, there's always a centripetal acceleration. If the circle is speeding up or slowing down, there's also a tangential acceleration. They're in different directions. They tend to be wildly different in magnitude, but they're really easy to confuse. So you have to be sure you understand what the difference of these things is. Okay, so that's the physics behind what we're doing today. What we're going to do now is take a little break and come back and look at the equipment that we will use to measure these things. This is stuff we haven't used before, and we have to talk about how to set it up and how to get Audacity to measure an angular velocity. So, we'll be back in a second. Okay, now it's time to get out this new equipment and see how this works. The new equipment is a nice big lawnmower wheel. This is nice and heavy and has pretty good bearings, spins for a long time. And for an axle with it, we're going to use the large bolt and the washer. And what I want you to do is put the washer on the bolt, slide it through the hole in the center of the lawnmower wheel, and then put the nut on the other side just to keep it all from falling apart. So we sort of loosely screw that on. Now to hold it up so it can rotate freely, what we have in the studio here are two of these nice boxes. These work really well. You can use books or turned over drawers or whatever you can find that will hold the wheel up and let you spin it in such a way that it doesn't wander off or anything like that. Okay, so we put the wheel in between the boxes. We have our microphone here listening to it. The one thing left is to figure out how to make it make a noise. And to do that, you take your basic ordinary push pin and just stick it right in the side of the wheel. The wheel's made out of solid rubber. You're not going to puncture it or anything like that. Put it in the side and then take a card. This is the Joker. You can use any card you want. Business cards work well. Anything rigid, and sort of hold it so that when the push pin goes around, it will hit the card. And what we're going to be doing is recording the sounds made as the wheel turns, and you get sounds like that. These sounds generally come out pretty nicely on microphones, and they're nice and easy to count with Audacity. So that's what the new equipment is like. This is what we're going to be using for the next two labs. It's worth figuring out how to do it and set it up. All right, now it's time to actually do the experiment and see what we find. What we're supposed to do in this series of experiments is measure the rotational velocity of the wheel under several sets of conditions and try to measure how the wheel slows down. So we'll be measuring the rotational velocity and measuring changes to the rotational velocity. And to do that, we're going to use this setup with the clicker and the card and Audacity running. Let me start Audacity right now. Okay, Audacity is now running. And for step A, what I'm supposed to do is give this thing a kind of medium-sized push and get about 8 clicks. So we'll try that. Okay, that was 10 clicks. And it looks like I got some very nice data. Stop, okay. So now we go to Audacity and we sit down and try to measure when these clicks happened. Now, every click corresponds to the wheel rotating all the way around. I only have one pin in there. And theta starts at 0 here. And for the first click, it goes all the way around. It increases by 2 pi. The next click, it increases by another 2 pi, and so on. Okay, what we do now is go over to Audacity and find the times of the clicks. And you've done this many times, so we're not going to make you watch me do it. And we're just going to cut to the chase and get the numbers up on the board. Okay, I have now extracted the numbers from Audacity and put them on the board, what we have here is the number of the clicks. This is the angle that has been rotated through at each time. You see it just goes up by 2 pi every rotation. And this is the time that I got from Audacity. What we're going to have to do is take a look at the change in theta divided by the change in time for each pair of clicks. And that will be the angular velocity that we're looking for. It should slow down as it goes. That number should not be constant. It was quite clearly slowing down while it was rotating. What we're trying to do is to put a number on that angular deceleration. So here we are. I've put these numbers into the spreadsheet and are ready to do the calculations. When I put in the angles, I didn't type out all these digits. Instead, I used the fact that Google Docs knows what pi is to 14 decimal places, and we'll use that. The first one is just 2 times pi, and after that, I used a formula that multiplied the top one by the click number, and that gets you pi to many, many digits, way more than you could possibly ever need. So, okay, I have the raw times typed in. I have my angles. Let's figure out what the angular velocity is. We'll make a new column for angular velocity. And in this column, what I want to have is the change in angle divided by the change in time. So I'll use a formula to do that. Take the column down minus the angle there and divide that by the change in time. And that will do the trick for me. Then I can just take this formula and drag it downwards, fill up this for every single one of these things. And it does. Let me see, the last one is a bit spurious because it's referencing the column, the line below it, which doesn't exist. So I'm just going to blank that one out. And now I have a column of angular velocities. You can see that it starts with an angular velocity of 12.29 rads per second. That's ticking along pretty quickly. But as time goes by, that number decreases, and that's the wheel slowing down. The angular velocity is decreasing, so that by the end, it's down to 5.36 rads per second. It's less than half of what it had at the beginning. We can take these angular velocities and the times and use that to calculate the angular acceleration in another column. So we'll do that, angular acceleration. The angular acceleration is going to be done with another formula. It'll be equals the change in angular velocity. So that minus that divided by the change in time. The change in time we get out of this column, that minus that. It'll give me a number for angular acceleration. Once again, I can just drag that down. And one more time, the last row doesn't really make much sense because it doesn't have a time for that. So we'll do that. And the angular acceleration wobbles around a bit. It goes from minus 1.5 rads per second squared. And the lowest one is minus 1.02. So this is wobbling around a bit, but they're all reasonably consistent. They are settling in a value about minus 1.2 rads per second squared. So that's what we need from this experiment. We've got the angular velocities, we've got the angular accelerations. That was what I wanted. What I want you to do next is to try this for a number of different conditions. Try it, giving it a nice hefty spin at the beginning, and then try to increase the angular deceleration by putting your fingers on either side and slowing it down as it goes. So I want you to sort of squeeze the rotating wheel between a couple of washers. That should make it slow down more, increase the friction, and you should get a higher angular acceleration. That's what we're doing this week. I want you to go ahead and try it now and send me the results.